Hey there guys, Mr. Carlson here. Let's talk about oxidation reduction reactions. Sometimes these reactions are abbreviated as redox reactions. So that term redox just comes from oxidation reduction. And so for a redox reaction, we're looking for a reaction in which electrons are transferred from one thing to another. So a good example of that would be sodium metal, solid sodium metal, combining with chlorine gas to make sodium chloride. If we look at this, we're making this ionic compound, and we can see at the beginning sodium starts as an element by itself, elemental sodium and elemental chlorine. So at the beginning, neither of these have a charge. They're not +1 or -1 or anything yet. But once they react, they transfer electrons. Sodium gives up an electron to chlorine. And so chlorine gains that electron, becomes -1. Sodium has lost that electron, becomes +1. We've already talked about these before. And so then we make that compound in which they have those charges to make a neutral compound. This is an example of a redox reaction where one thing loses electrons to another thing to make something else. So all those kind of like reactions where we're making an ionic compound, those would all be examples of redox reactions. But not all redox reactions deal with ionic compounds. So we are going to have to use a system to keep track of electrons. And the way we do that is we use what are called oxidation numbers. So an oxidation number we can kind of think about is like a charge. Like a charge. So with ionic compounds like these up here, we've already learned how to use the charges for ionic compounds to figure that out. But not all reactions are going to be dealing with ionic compounds, and for things like covalent compounds and stuff like that, we have to use these oxidation numbers to keep track of what thing is losing electrons and what thing is gaining electrons within a reaction. So here are the rules that we're going to use for that. The first thing is an atom in its elemental state is always neutral. So just like we saw up here, when something is an element by itself, like sodium here, it's going to be neutral. It's not going to have a charge of anything. Same thing with chlorine here. In its elemental state, it's going to be neutral. So an element by itself is always going to have a charge or an oxidation number of 0. Number 2, the oxidation state for a monoatomic ion is the same as its charge. So just like above in that example there, like if I'm given this compound magnesium chloride, these two monoatomic ions, I know that the charge on magnesium here is going to be +2, and that chlorine is going to be -1. Here, sodium is going to be +1, chlorine is going to be -1. In this one, calcium is +2, and oxygen is -2. So those rules for those monoatomic ions are still going to hold true, just like we've been doing. Number 3, oxygen is usually -2. So typically, when we're assigning oxidation numbers, when we see oxygen, we can usually automatically put it as -2. The only exception to that is going to be if you see peroxide, which you're probably not going to see a ton of. But if you do, in that case, if you look at this, you've got O2, and the charge of this is 2-. So that means each oxygen in there is actually -1, right? So you have 2 oxygens, and the overall charge of that molecule is -2, so therefore each oxygen is actually -1 in that case. So when you have peroxide, the oxidation number of oxygen is -1. That's the only exception. Every other time, no matter what, oxygen is going to be -2. Number 4, in covalent compounds with nonmetals, whenever you have hydrogen, so when hydrogen is in a covalent compound with a nonmetal, it's typically going to be +1, okay? Number 5, fluorine is always -1, so no exceptions to that one. Whenever you see fluorine, doesn't matter what it's with, it's always going to be -1 for a charge or an oxidation number. And then this last one down here, the sum of the oxidation states for a neutral compound needs to add up to be 0. But if you're dealing with a polyatomic ion that has a charge, that means your oxidation numbers for each thing within that polyatomic ion, they have to add up to equal the charge. So for this last one here, we'll do a couple examples. Hopefully that makes a little more sense. So let's do these ones down here. So what we want to do is we want to assign for each thing here what's the oxidation number, or in other words, what's the charge that each thing has within that compound, okay? So looking at CO2 here, so typically if we're going to assign oxidation numbers, let's come back up here for a second. What I'm going to look for first, I'm going to look for, is it an ionic compound to where I can just kind of easily use the group number to figure out what the charges are. So that'll be the first thing. If I see an ionic compound like one of these, then I can just easily assign what the charges are. If I'm not dealing with that, then what I'm going to look for is, do I have oxygen, do I have hydrogen, or do I have fluorine? I'm going to look for one of those three things first, because that's where I'm going to want to start to assign my oxidation numbers. So in that first compound, CO2, I'm going to look at that oxygen first, and I'm going to assign it as a -2 right off the bat. So for CO2, I know that oxygen here, actually, you know what I'm going to do? I'm going to use a different color here for a second. So for that oxygen there, -2 is the oxidation state on oxygen. Now, I've got 2 oxygens in there, right? So the total on that is going to be -4. That means whatever this carbon is needs to balance out that -4 in order to give me a neutral compound, right? This is not a polyatomic ion. CO2 is just neutral. So these two things, when added together, the oxidation states that I have here, added with this, need to cancel out to be 0. So if the total for oxygen here, since each oxygen is -2, a total of -4 coming from the oxygens, that means this carbon must be +4. So my oxidation state for carbon in this CO2 molecule is +4, and my oxidation state for oxygen was -2. So don't use the total that you have for oxygen. You want to put what is the oxidation state on just a single oxygen within there, which is going to be -2. Let's take a look at this one. NO3, now this is a polyatomic ion. So that means all my oxidation states need to add up to give me an overall charge of -1. So once again, I see oxygen is the first thing here. So that I know I'm going to right away assign as -2. Now let's do the total again, because I've got 3 oxygens. So -2, and each, I've got 3 of those, so that's a total of -6 coming from those 3 oxygens. That means this nitrogen now, what does this nitrogen have to be? And what I have to think about is this, and whatever my oxidation number for nitrogen here is, needs to add up to give me a total of -1. So that means that that nitrogen must be +5, right? Because a +5 plus a -6 would leave me with a -1 left over. So therefore, in this compound, nitrogen has an oxidation number of +5, and oxygen, as always, is going to be -2. Okay? Let's come over here. Now this one I see as an ionic compound. I've got a metal with a polyatomic ion here. So in this case, the first thing we can do is I can break it up into its ions here. Now CO3, you may or may not have this memorized, but that's carbonate, and carbonate has an overall charge. I'll write it over here. CO3, if it was by itself, is a charge of 2-. So if I've got 2 coppers here bonded with this CO3, overall, this whole thing is a neutral compound overall. So that means if this CO3 by itself is 2-, that means these 2 coppers need to add up to be 2-. So therefore, each copper must be -1, right? If each copper is -1, I've got 2 coppers, that's a total of -2 to balance out the 2- charge on here. So I'm going to write down here that copper must be +1. Now, we could just leave it at that. We could leave it as copper is +1, and then the carbonate is -2 if we wanted to look at just the ions. Now, in certain problems, you may have to look at if this, in the reaction, this breaks up, then you may have to look at the individual oxidation numbers. So what we could do is I could say, well, okay, the oxygen I know is going to be -2. I've got 3 of them, which is going to be a total of -6. So what does this carbon have to be in order for this total of the oxygens? What do I have to have here? Plus the -6 to leave me left over with -2. So this would have to be +4 in that case. So therefore, carbon is +4 and oxygen -2. So we could have just looked at it as the ion, CO3 is -2, the copper is -1, but if we wanted to look at the carbon by itself and the oxygen, we would have to look at it like this, using its ion. Let's take a look at SF6. So fluorine now is where I'm going to start. So remember, it's oxygen, hydrogen, and fluorine if we have those. So fluorine, in our rules up here, fluorine's always -1. So I'm going to come back down. -1 is the oxidation state. The total then for the fluorine, since I've got 6, is -6. This whole thing is neutral. There's no charge up here. So that means if the total from the fluorines is -6, that means my sulfur here by itself needs to be +6. So sulfur in this compound is +6, and fluorine is -1. Over here, I see oxygen again. I'm going to start with that one. Oxygen we label as -2. The total is going to be -10. So that's the total from these, because I've got 5 of them. 5 times -2, the total is -10. Now I've got 2 nitrogens, so I got to ask myself, what's the charge on each nitrogen going to be? Because I've got 2 of them. What is the charge on each one going to be to add up to -10, right? Or sorry, it'd have to be positive. But so each one is going to end up being +5, right? Because a +5 for each one would give me a total of +10 to cancel out that -10 from the oxygens. So nitrogen has an oxidation state of +5, and oxygen is -2. And the last one, same thing. So oxygen, right off the bat, -2. Now I've only got 4 of them, so that's -8 for the total. Now notice how the oxidation numbers can change, right? So nitrogen here, once again, I've got 2 of them. What's the charge on each one going to be to cancel out that -8? And so each one is going to have to be +4 in this, +4. And so now in this compound, nitrogen is not +5 like it was here, it's actually +4. And oxygen is still -2. So those are the rules that you're going to follow when you're assigning oxidation numbers. In the next video, we'll take a look at actually doing this with some reactions to figure out what's being oxidized and what's being reduced.